And we are moving on to 3.2, determining empirical and molecular formulas. So in this section, we're going to compute the percent composition of a compound, determine the empirical formula of a compound, and determine the molecular formula of a compound. So let's first talk about percent composition. So this is the percentage by mass of each element in a compound. So we kind of talked about this, we touched on it in chapter 2. So for example, if we have a 10-gram sample of a compound and we find that it has 2.5 grams of hydrogen and 7.5 grams of carbon, percent hydrogen is equal to the amount of hydrogen divided by the total compound. So 2.5 grams of hydrogen divided by 10 grams of the compound, 25%. And then the rest is carbon, 7.5 divided by 10, 75%. So as long as you are given the masses of each element in a compound and then the total mass of the compound, you can figure out its percent composition. Now we can also do this if we know the formula of a compound, even if we weren't given the masses. So for example, let's say we have ammonia, NH3. The percent nitrogen is going to be equal to the molecular mass of nitrogen divided by the molecular mass of NH3. Same for hydrogen. Though there's 3 hydrogens, so it's 3 times 1.008 divided by the total mass. So you can do this even if you don't have the actual masses, you can use their molecular formulas. Now let's talk about getting percent composition from a molecular formula. As an example, using aspirin here. We're told it has the molecular formula C9H8O4. And to get its percent composition, we need the masses of carbon, hydrogen, and oxygen. So what we do, just to kind of talk a little bit more in depth, we looked at ammonia very quickly, is we're going to use the molar masses. So we have 9 carbons. We can say we have 9 moles of carbon in 1 mole of this aspirin. Remember, it's C9H8O4. So for every 1 molecule of this we have 9 atoms of carbon. And we can scale this up to moles. For every 1 mole of aspirin, there's 9 moles of carbon. So we have 9 moles of carbon times its molar mass divided by the molar mass of aspirin times 100 gives us our percent carbon. We have 9 times 12.01 divided by the total molar mass, 180.159 times 100. And we get 60% carbon. We do the same thing for hydrogen. There's 8 hydrogens times its molar mass divided by the molar mass of the whole compound. We get 4.476% hydrogen. And notice we're doing 4 significant figures because that is what our molecular mass sig figs are. And then oxygen, same thing. We have 4 of them times its molar mass of 16 divided by the total. And we get 35.52% oxygen. So these calculations get a little bit repetitive, but it ends up being good practice. And then what you should also notice as a way to check your work is that when you add up the percentages, they should come to be just about 100%. It might be a little bit off, and that's just because of rounding, but it should be pretty much right there. So now let's talk about determination of empirical formulas. So if you recall, the empirical formula is the lowest ratio of atoms in a compound. So if you have something that's normally, C6H6, that would be the molecular formula. The empirical formula would be CH. So we can figure out an empirical formula based off of the masses of the elements in it. So we start by taking the element masses and make them into moles, divide each number of moles by the smallest number of moles, and then if we need to, multiply by an integer to give the smallest whole number ratio. It sounds really complicated, but it's a lot easier when you see it in practice. This is one of those things that just describing it honestly sucks. So let's look at some examples. So let's start with a compound that is determined to have 1.71 grams of carbon and 0.287 grams of hydrogen. So we're going to start by taking our grams of carbon and turn it into moles. So 1 mole of carbon per 12.01 grams of it. We have 0.142 moles of carbon. Do the same thing for hydrogen, turn it to moles, from grams to moles, and we get 0.284 grams. The lowest number of moles is that from carbon, so we're going to divide both of these by 0.142. They like to do it where they put like C.142, H.284, that's fine too, and then divide it with the subscripts. It really doesn't matter how you do it. So we get 1, and then we get 2. So then this tells us that there's 1 carbon, 2 hydrogen. That means our formula is CH2 for our empirical formula. Here's another one. We're told 5.31 grams of chlorine, 8.40 grams of oxygen. Okay, so we're kind of skipping the looking up the molar mass, changing them to moles. You guys can go from mass to moles by now. So we end up getting 0.150 moles of chlorine and 0.525 moles of oxygen. So we divide both by the 0.150. And what we find is the oxygen comes out to be 3.5. We cannot have 3.5 atoms. If we could, we would win like all the Nobel Prizes. So what we need to do, we see this ends in 0.5, and that's generally what you're going to get. Occasionally, you might get one that ends in like 0.3, and then you would multiply times 3. You want to get it to a whole number, so we're going to multiply both these subscripts times 2. 1 times 2 is 2. 3.5 times 2 is 7. In general, when I'm writing test questions, I'm not going to give you one more complicated than a 0.5 if I need to apply. So there's a nice little flow chart that your book gives you. You just look for what you're told to start with and how to get there. You have some A and X. Go to moles, divide by the lowest number to get your ratios, and then you go to a formula. You can also get empirical formula from percent composition. And it's actually pretty much the same. The only difference is you're given percents of each element. So what you're going to do, you're told, oh, it's 20% carbon, whatever, and all the other percents, you just assume it's 100 grams. So you take that percent sign and you switch it to a G, and then everything's the same. For example, fermentation, produce ethanol, we get 27.29% carbon and 72.71% oxygen. So we're gonna, if it's a part of 100, then that means it's 27.29 grams of carbon and 72.71 grams of oxygen. You're just assuming 100 for your total mass. So you just go, no, that's now a gram. Convert your grams to moles, divide by the lowest number, just like you've done. And you get 1 for carbon, 2 for oxygen, CO2 for your empirical formula. Yay, we did it. And this is what these fermentation bins look like. If you're under 21, don't look. All right. So let's talk about now figuring out molecular formula. So now we've done empirical formula, the lowest whole number ratios. Now let's go to molecular, which are the actual formulas. So you do all the steps to find the empirical formula, and then you find out that the actual mass, like you're told that the molecular mass is different. It should be higher than the empirical formula. It's not going to be lower than empirical. So that means you have to scale up your empirical formula. The amount you scale it up by is found by taking the molecular or the molar mass, whatever the actual molecular or molar mass is, divide it by your empirical formula mass that you just found. And then you're going to get some should be pretty much a whole number. And you're going to multiply each subscript by that number. Let's look at examples. We're told a compound has an empirical formula of CH2O, and you could calculate that out, and you see it has a formula mass of 30, but it has an actual molecular mass of 180. So you take that 180 divided by 30, and you get 6 formula units per molecule. So that means we're going to take this formula of CH2O and multiply each subscript by 6. So that gives us C6H12O6, and that's our molecular formula. So here's another example. Let's say we're talking about nicotine here. Don't smoke it. Interestingly enough, it's in the nightshade family. Nightshade is poisonous. So it has 74.02% carbon, 8.710% hydrogen, and 17.27% nitrogen. And we're told that 40.57 grams of nicotine contains 0.2500 moles of nicotine, and we want the molecular formula. So the first thing we should do is take all these percentages, turn them into grams, and get their moles, which is what we have done down here. So this is step 1. Okay, so carbon to moles, hydrogen to moles, nitrogen to moles. Our lowest number of moles here is the nitrogen, 1.233. So everything is going to be divided by 1.233. Okay, so then when we do that, we see that the carbon comes out to be 5, hydrogen 7, and of course nitrogen 1. Okay, and they put the work here. You can see 4.998, 6.994. Those are way close enough to be 5 and 7. Okay, so don't freak out if you don't get an exact number. It all has to do with rounding. It's all good. And now we can also calculate the molar mass of nicotine, because we're told we have 40.57 grams that is 0.2500 moles. So we do the grams, we divide it by moles, and we get its actual molar mass, 162.3 grams per mole. So now we know the actual molar mass, and we got our empirical formula of C5H7N, and we can calculate that molar mass to be 81.13. Okay, from 5 carbons plus 7 hydrogens plus 1 nitrogen. Now we're going to divide our molar mass by our empirical formula mass, and we get 2 formula units. So that means we need to multiply our empirical formula subscripts by 2. So we get C10H14N2 for the actual molecular formula. So you can see these problems get a bit more involved as you go. But as long as you take it step by step, don't freak yourself out from all the information given. I think that tends to be what scares people the most, because there's just all this information thrown at you. Break it up into individual small pieces and then see how they come together in the end. And then you've got it. Practice makes perfect with these, and I know you guys can do it.